Hello, everyone. My name is Garrett, and I am a math tutor at the DLASC. And today I want to be going over how to solve differential equations using variation of parameters method. Okay. So firstly, let's think about this equation here. Let's say y double prime minus 4y prime plus 1 equals t to the 1/2 e to the t halves. All right. So how do we solve this differential equation using the variation of parameters method? The first thing I want to show you is the idea or the end game that we are trying to reach is y of t equals h of t plus p of t. All right, that is the end game. That is our goal that we want to reach, right? All this is your y of t, your h of t is going to be your homogeneous solution plus your p of t, which is your particular solution. But we're going to come back to that. First, we're gonna start by solving this. The first step. Excuse me. This is not for y prime, but this is for double y prime. And yes, that's how I do it. So the first step to solve this equation is you want to put this in standard form. Okay. And in order to do that, you want to make the y double prime at the front. You want to isolate that and just have that. So the way we can do that is we can divide everything by 4. So if we divide everything by 4 here, we end up with this. Y double prime minus y prime plus 1/4 equals all of this on the other side divided by 4. Okay. Now, that is the first step. Every time when you solve this using variation of parameters method, the first thing you want to do is put it in standard form. The second thing you want to do is to solve the homogeneous equation. So solve h of t equation. And what is the h of t equation? Your h of t is your homogeneous, right? And that is simply just saying that your homogeneous equation is the same thing this is at the front, but equal to 0. So it's going to be y double prime minus y prime plus 1/4 equals 0. Okay. And then you just solve this. So the method of solving this is I'm going to use is convert, everything to its roots. So we're going to say y prime is r squared minus r plus 1/4. Okay. And if you were to factor this would simplify to r minus 1/2 times r minus 1/2, right? Because negative 1/2 times negative 1/2 is negative 1, and then you multiply those, that'll give you positive 1.4, or 1/4. So what we end up having is we have r equals 1 with a multiplicity of 2, okay? Or 1/2, the multiplicity of 2, rather. And so our h of t here is equal to c1 e to the 1/2 t plus c2 e to the 1/2 t. Okay? And this is just the standard format for solving homogeneous equations. You find your roots, and your roots become c1 e to the rt plus c2 e to the rt. Oh, I'm sorry. And we want to make this linear independent because they're the same. we're going to remove this C2 and make sure to keep its linear independence, we put the T here, right? That's the format when you have something that has a multiplicity of 2. When you have 2 roots that are the same number, remember to put that T. So that is step 2, okay? So let's go ahead for step 3. You want to remember our y of t equals h of t plus p of t, right? That's the thing we need to remember. We have our h of t right here. Now we need to find our particular solution, our p of t. And the way we do that is we're going to make p of t, and this is the way we use variation of parameters method, is the same thing as saying c1 of t to the e1/2 t plus, let me write c2 of t to the e to the 1/2 t. So all we did here to find a particular solution is what we took a homogeneous solution and added c1 and c2 were functions of t. That's the only thing we're doing here. And that is the method of, finding our particular solution. And here is our rule 3, right? Our step 3 in this case. So this is what our particular solution is going to look like. Step 3 is we're going to assume p of t to form a system of equations. Okay, as follows. Okay, so what we're going to do is we're going to have this here equal to 0 for our first equation. So we're going to just go ahead and write this down. C1 of t e to the 1/2 t plus c2 of t to the e1/2 t equals 0. And for our second equation, we're going to take the derivatives of this and then make that equal to our non-homogeneous equation up here. We'll call this n, right? This t to the 1/2 e to the t halves over 4. So that's what we're going to do, okay? So we'll say c1 of t, and then, the derivative of e to the 1/2 t is just 1/2 e to the 1/2 t, right? We just bring this to the front, plus c2. And here we're going to have to do a product rule because you have a t and the 1/2 t. I'm just going to go ahead and just write it real quick for us. And if you want to do the work, you can, but just trust me here. The derivative of t to the 1/2 t is just 1/2 t e to the 1/2 t plus e to the 1/2 t. And this is all equal to our n, which is t to the 1/4. T to the 1/2 e to the t halves over 4, right? And this is our system of equations here. And now all we want to do is we want to solve this, okay? And the way we will solve this is, there's different methods you can do. You can put this into Kramer's rule and solve it. But the way we're going to do it is we're just going to solve it by some simple algebra here. And we're going to multiply the top by 1/2. You know what, rather. Okay. Multiply the top by 1/2 and then add. All right. And what's going to end up happening is you see you have our negative 1/2 because we want to cancel out these two here. We want this to happen, so this will be negative 1/2. And then what you do here is this is going to add this negative 1/2 over here. And you'll see these will cancel out, right? This and this will cancel out when you multiply that negative 1/2 here. And then you're just left with this here, right? And so you can rewrite this when you add as you have 0 plus C2 of t, and these cancel out, and so you have plus 1 e to the 1/2 t. And then you're going to add the 0 when you multiply that negative 1/2 to this over here, right here. That just zeroes out, and so you're just going to have the same thing over here because that plus that equals the same thing. I hope you're following me here. And so now you have this C2, so you can isolate this. And what you have here is this E will divide, if you could see that. And when it divides out, when you divide this e to the 1/2 t and divide it over on this side, what you end up getting is they end up just canceling out, right, algebraically. Because this is e to the 1/2 t, same thing. So that just makes it a little bit more simpler, and you're left with C2 of t. Well, okay. Well, I missed this part, but C2 of t equals t to the 1/2 over 4. Okay. I do want to mention, I forgot to say this, but this is all your C1s and C2 in your equations are primes, okay? Because for our last step, these are all C prime 2 of t, C prime 1 of t. That's not too important. Just remember, that's just to remember because the last step is we integrate it, okay? But you'll see that in a second. So we have our C2 of t. So now we could plug that in to find C1 of t. And it goes something like this. Let's say we have C1 of t times e to the 1/2 t plus t to the 1/2 over 4 times t e to the 1/2 t equals 0. This is our first equation here, right? That's all we're plugging in here. And so here, what we do is we can factor out and divide by 0 here, this e to the 1/2 t. So these kind of cancel out. And you're left with C1 prime of t, don't forget my primes, my goodness, of t equals, and we can just bring this all over here to this side and make it negative, right? T to the 1/2 over 4. It's 3/2 because you have this t also here. So you multiply that t to the other one and it becomes 3/2, right? But this should all make sense, right? So now you have your C1 prime and your C2 prime. And I guess I kind of missed the last step, obviously. I kind of gave it away here. Nope, zoomed in too much. But our last step here is now that we have C1 prime of t and C prime of t, we are going to integrate. Okay? And now that we have this, these are simple integrations, right? We take the integral, well, C1 of t equals the integral of t of 3/2 over 4. And this is an easy integration. I'm just going to let you do it, but quickly, I'm just to save some time. This converts to negative 1/10 t to the 5/2 when you integrate this. So this is your C1, okay? So this is our C1, right? Our C2, when we integrate, we are going to take the integral of t 1/2 over 4. And this is 1/6 t, 1/6 t to the 3/2. And that is our C2 of t, right? And so now we have our C1, we have our C2 of t, and so this comes back to our particular solution right here, right? Our particular solution says this. And so if we plug in what we have in our particular solution, we end up getting, let's go ahead and put this in here. We end up getting P of t equals, and we go back down, we look at our C1 and our C2 is these things. So we can say that P of t equals -1/10 t to the 5/2 times E 1/2 t plus 1/6 t to the 3/2 times t e to the 1/2 t. And we can go ahead and simplify this. We can rewrite this because we have our t's over here, right? And they're multiplied. So we can rewrite this as P of t simplified is -1/10 t to the 5/2 e to the 1/2 t plus 1/6 t, and we add the exponents here, 5/2 t, and then e to the 1/2 t. And this is our particular solution. And so let's remember the end game here, right? Y of t equals your homogeneous versus your particular. We have our homogeneous solution right here, right? We have our particular solution over here. So the end answer result is y of t equals, and then we just plug in. We just plug in all of this, right? Plus C2 t e to the 1/2 t plus all this. And actually, because these are all the same exponent, I mean, it's the same base here, right? T to the 5/2 e to the 1/2 t plus another t to the 5/2 e to the 1/2 t. We can add this and combine it and call this just 1/15 t to the 5/2 e to the 1/2 t. So that is our homogeneous solution times our particular solution, and this is at the end of the day our final answer. Okay, but the steps of variation of parameters, if we come back here to the start, is you want to put it in standard form. You want to solve for your homogeneous equation, right? Solve for that. And right, remember what we're ending at is the homogeneous times particular. So then we make the particular functions of t. We put them in a system of equations where, you know, the first term are the first couple terms are 0, right? And then our last term is our non-homogeneous, is equal to our non-homogeneous side. We solve that system. We integrate that system, and then we just plug it into the P of t, and then plug it all in to H of t plus P of t to make our differential equation. It's a lengthy solution, but if you can memorize the steps and follow those, it always works. And it works for a lot of different equations. It doesn't just, like for some of the other methods, just work, you know, only for particular equations, and some of them you can't use the rule. This one is a lot more versatile and a lot more flexible. So just remember the steps and you should be good. So happy studying, y'all.